I have to point out I am disappointed that none of our non-calculus students wanted to come and hear about the particle in the box. It really is very curious and interesting. So we've already gone through the first couple slides, but I wanted to do some work now on this because I just quickly introduced it. So the separation of variables from the time dependent to the time independent Schrodinger equation. You can only do that if the potential, well, there are ways, special ways, that, special circumstances where it can be done. But if the potential energy function is not a function of time, then you can separate. If it is a function of time and not position, you could also separate it, but that's far, far rarer type of idea. So how does that work? Well, you start by just writing your time-dependent Schrodinger equation, replacing psi with the product. So notice the capital psi versus the lowercase psi. The capital psi is a function of both position and time. The lowercase psi is just a position. And so we write the equation here, and notice that I put in blue everything that has to do with time, and in red everything that has to do with position. Because these are partial derivatives, go ahead, Gabriel.
The red part of that function to the right of the partial of t, is
yes.
That
that's d second dx squared of psi of x.
Psi.
Yeah, that's psi. I can see what you're saying. It's the same thing. All three of them. My handwriting is consistent. Okay, so because those are partial derivatives, a partial derivative with respect to x will not affect a function of time. And likewise, a partial derivative of time will not affect a function of x. So we can freely rearrange this to move the red stuff past the blue or the blue stuff past the red, as long as the derivatives are going to operate on the variable that is of the same color here. Now, this is not separated, but it leads to the next step. And the next step is sound for all cases except for the transitory zeros. That is, we're going to divide everything well, I'll separate it. Yes. So I divide everything by the same thing. Now note, if those are equal to 0, you have a division by 0 error. But usually they're not, so it's considered a legitimate move. Now when we do that, we have canceling that occurs. So I'm going to have here the psi of x is canceled. Here the phi of t is canceled. Here the phi of t canceled. So what do I have on the left-hand side? I have and on the right.
Why is the psi of x not canceled in the third term?
Actually, it does. You're right, but I'm going to leave it there because I'm going to multiply it back. Okay. You're right. It does cancel. Because the v, unless the v has a derivative in it, I suppose. Since it's a function of x, it could have a derivative or integral in it, and then it wouldn't cancel. So that's why, because it's being operated on still. Okay. On the other side, now, the left-hand side is purely a function of time. The right-hand side is purely a function of position. So that means that both sides have to be constant, because if I change time, but stay at the same position, I can't have a change in the right-hand side. If I change position but don't change time, I can't have a change in the left-hand side. So they're both going to have to be constants. So we take this and we just say arbitrarily it's equal to a constant, and that constant turns out to be the energy E, so I just wrote E. So that gives us two equations now, the left-hand one and the right-hand one. So I'm going to write those two equations, and then on the next screen, of course, we have them printed out for you. So I H bar now notice I multiplied across by that phi, so it's not the denominator anymore. And then for the other equation, excellent. I completely changed colors. Blue is time, now red is time. Don't pay attention to the colors except for as distinguishing one thing from an, well, yeah. Okay, there I combined the E and the V. And so there's two equations that came from the one time-dependent Schrodinger equation. So this left one just gives me the time variation for my wave function. The right hand gives me the spatial variation. Gabriel.
Could you step to the side just a little bit? And then what was the I again at the beginning of the time dependent?
This here,
Yes.
that's the imaginary number I. That was part of our operator. So switching to the next page, we just have those written in a more legible fashion. So this one here, I didn't move the V across, but that's the time-independent Schrodinger equation on top, and then the time-dependent portion on bottom. So how do we solve these? Well, if I take this time-dependent portion, that's easy separable, right? That's something that you can all do. So you separate it, you have d phi over phi is equal to E over I H bar dt. We often don't like to put 1 over I. What do we put instead? Since Nathan had to take the ACT on Sunday, we've just been going over this at home. It's negative I. Because if we multiply top and bottom by I, we would have I over I squared, but I squared is minus 1, minus I. So another way of writing this is equals minus I E over H bar dt. So you integrate both sides, and you're going to get an equation that says psi equals, I didn't put a constant here, but it could have any constant out front. So that's the solution you get for that time variation portion. Right, because you recognize you get natural log, and then because it's natural log of psi or phi over phi 0, that's where you get the phi 0 from. Now, how many people are comfortable with that? That utilized Euler's relation that says e to the I, well, let me not use that. And so in this case, the argument theta was minus E over H bar T. And cosine of minus theta is the same as cosine of plus theta, so that's why the cosine sign stays positive. Sine of minus theta is minus sine of plus theta, so that's why the sign changed in front of the sine term. So that's something we can use to change from an exponential with an imaginary number in it to simple sinusoids, because we understand simple sinusoids better. I do, at least. and I expect most of you do too. This is something that in our class we're only looking at to see that it exists. In most classes, that's what we do. Even in quantum physics, we usually start by saying, ignore this. We just have to know it exists. We can find a time dependence for it. What is going to matter to us is the stationary states, the time independent results. So looking at the time independent Schrodinger equation, we have the time independent Schrodinger equation, and I'm going to apply it specifically to the particle in the box problem, where we have infinite potential energy outside the box, zero potential energy on the inside. And so taking that, I rearranged my Schrodinger equation here. Notice I moved the 2m and h bar across, along with the minus sign. And now from differential equations, which I don't anticipate that you've taken. I know, Jonathan, you're in it now. Is that right?
No, I'm not.
Oh, you're not? You took it last semester then?
No, I didn't.
I thought you, were you planning on it?
I'm not in high school.
Oh, okay. I thought that before registration, your dad was saying he's going to be taking differential equations in the fall.
No.
Okay, I misunderstood.
Nope.
Doesn't matter because I don't anticipate it. So you're not expected to be able to solve this. Instead, I simply give you the solution has this form. So we have a second derivative, so we have to take the second derivative of that form and plug it in and see what falls out. So what's the second derivative of this psi function? Yeah. So I'm just going to plug that in. And so that would give me k squared e to the kx equals minus 2m over h bar squared times e minus v e to the kx. Well, this is kind of trivial now. What does k have to be? This is trivial. We're not done. The problem's not trivial. What does k have to be here? It's going to have to be that k squared, so I'll put the square here, is equal to minus 2m over h bar squared e minus v. So that means k is equal to the square root of minus 2m over h bar squared times e minus v. Now we go ahead, Carrie.
Why did you put the e to the kx on both sides?
Because the second derivative of psi, k squared e to the kx.
Yeah.
Oh, and I forgot to write the psi. That
Okay.
I didn't notice that I'd forgotten to write it. Thank you. So we have something here. K is simply dependent on the energy and the potential energy. Okay, let's look at our different regions. Our different regions are region Roman numeral 1, region Roman numeral 2, and region Roman numeral 3. In region 1, V is infinity. So what is E minus V if V is infinity? It's just minus infinity. The E becomes immaterial because the energy is not going to be infinite. So we're just going to have minus infinity for that E minus V, which means in region 1, I have K is equal to square root of minus 2m over h bar squared times minus infinity. Well, the minus and the minus makes a plus, so it's equal to the square root of infinity, which is, but Okay, it could be plus or minus infinity. There are two results. So I have two answers here. I have answer 1, so I put a plus sign, is equal to e to the infinity x. And then I have the second one, e to the minus infinity x. Now this is mathematical results. Now I put infinity there. What would you do if you were a mathematical purist? You would have k and you'd say the limit as k approaches infinity, right? That would be the mathematically pure way of doing it. Well, if we look here at region 1, I didn't point this out, but we're going from x equals 0 to x equals L for our box. So in region 1, x's are always negative, right? Yes. Always negative, which means that, well, I should have said this before I pointed that out. That means my total psi in region 1 is equal to some constant, so I'll put a plus times psi I plus a minus times psi I minus. And that's going to be equal to a plus e to the minus infinity for all x's plus a minus e to the plus infinity for all x's. Well, what's e to the plus infinity? It's infinite. We have a rule, and one of our rules is that we have to have a finite wave function. We can't have an infinite probability of it being at some location, right? And so to keep ourselves having a finite solution, we have a minus has to go to 0 to give a finite solution. And of course, what's e to the minus infinity? 0. So this term here just goes to 0. And as a result, what is psi 1? Now, does that make sense?
Where did you get the A's from?
Those were just random constants.
Okay.
We would have to determine them if they weren't zeros or,
But in that way, you were able to just get rid of the x term in the exponent?
No, I was applying, because I had the infinity, I used the fact that in region 1, x is always going to be less than 0, so it's always negative. And so then I took a negative number times minus infinity can always be a positive infinity.
Okay.
And likewise, a negative number times positive infinity is always going to be negative infinity.
Okay.
So that's how the x's disappeared.
Okay, thank you.
Okay, now this should make sense because going back to region 1, the potential there is infinite. My particle's never going to have enough energy to get there, so it makes sense that the likelihood of it being there is 0. Yeah.
What is phi representative of again?
What is, that's our wave function. That's the thing that tells us everything about the particle. And if I take that wave function and square it, it tells me the probability of finding it in some region dx. Now, technically, I should have gone ahead and left this as a plus e to the kx and gone on, but we're going to find that it's 0 for that term anyway. Question?
Okay, so the whole a minus going to 0 thing?
A minus has to be 0 because it's multiplied by infinity. You can't have a function that doesn't go to infinity if you have a constant multiplied by infinity.
Okay, so we're assuming it cannot go to it.
Right, that's a fundamental rule for a wave function. It has to be a function that is analytic, doesn't have infinities in it. So technically, I have this solution. Now let's look, if I'd gone to region 3, what's different about region 3 compared to region 1? Yes, the x's are positive, but otherwise we have basically the same rules. And so I would have ended up there with my psi for region 1, keeping for now the constant that's, or region 3, keeping for now the constant that's going to go to 0. And I will put c minus e to the minus kx. And what is k in this case? As we wrote, it's infinite. Right, it's silly to talk about the k here because it's infinite. So here I have the solutions written out. There's zeros for those two. I could have said, like I wrote, I could have put the a. Okay, now I forgot which one it was. It was. Yeah. And this would be. I would have had like that. The K's are different in the center region than they are in the two outer regions because your potential energy is different. And so the K's I have there are not the same as the K's in the center region. And because these are actually going to be zeroed out, I'm putting K prime for the two that we just did. And now let's do the one that matters, inside the box. Inside the box, I have V equals 0, so K is equal to the square root of minus 2me over h bar squared. Now, I get to this point and I notice that I did a difference in nomenclature, which it drives me crazy when I'm inconsistent. Does it drive you crazy too? Yeah. Okay, so here's the inconsistency. There's a minus sign there, right? And so that minus sign, what's the square root of minus 1? It's I. Everything is perfectly good that we've done except for what I should have done is not use K here. I should have used something like the letter B instead of K on this page. And then I would have had, here I would have had B equals this. And then I can define equals IK, where K is exactly the same thing, except for taking out the minus sign there. You can see that it matters. Hopefully my mistake illustrates a mistake that I made all the time so you won't make it when I was taking this class, and then quantum physics course I had to take afterward. That is not paying attention to the signs in my problem. And so the difference between what I now wrote as B and K is just the minus sign. So I have my solutions come out to be psi in region 2. We have two solutions. Why two solutions? Because when you do the square root, you always do get the plus or minus. And so this is equal to some constant, and I'm sure I used a different, I didn't write one there. Well, so some constant with a plus, e to the plus I kx, plus a constant with a minus, e to the minus I kx. That is, it's a linear combination of the two solutions. It's one solution multiplied by some unknown number plus the other solution multiplied by some unknown number. And then we're going to have to use what we call boundary conditions, what's going on at the boundaries, to find what those are. Question?
So in the solution, K is now positive.
Yeah, yes, K now is without the negative sign in the square root. Yeah, and I apologize for that. If I had done it right, you wouldn't have noticed the sign difficulties that can come up, but it would have been seamless and smooth. Now it's not seamless and smooth. So this is my solution in the region of the box. And when you look at that solution, you tend to say Well, that means nothing to me. At least that's what I see when I look at it. And so that's where we use the Euler relation. And the Euler relation means that we can rewrite this as b plus times cosine of kx plus I sine of kx plus b minus cosine of minus kx plus I sine of minus kx. Right, so I just use the Euler relation there for both. And then we combine the like terms. So this is going to be b plus plus b minus times cosine of kx. Cosine of minus kx is cosine of plus kx. That's why I just put them together. But as I said before, sine of minus kx is minus sine of plus kx. And so I'm going to have plus b minus I sine of kx. So there I have my solution. Hooray, huzzah, What do we have now? Well, we need to find what those constants are and move forward. So I think, let's see. Yeah, I left this at this point, so now we apply boundary conditions. What are boundary conditions? What does that mean to you? I'm going to add a page while I'm waiting for you to answer.
What's happening at your extrema?
Okay, what's happening at your extrema? What's happening at each edge of the box? So I have two boundaries. One is, I have two boundaries, one at 0, come on, and one at L. And so I'm going to have to apply my boundary conditions at each of those boundaries. Before I get to doing that, I am going to define new constants to make my life easy. I'm going to call this here, and there's where she crashed. Close the window, open back up. I have become much more adept with these crashes, I have to say. So I'm going to call this right here D. B plus B minus. Since B plus and B minus were just arbitrary constants that I don't know, I'm just going to assign the sum of them to the name D. Now these can be complex, so I am going to assign the name, the name G to B plus minus B minus times I. So I don't have to carry around the I anymore. It's included in my constant G. So this is just equal to D cosine of kx plus G sine of kx. Now let's look at the boundaries. So let's look at, so I have look at our boundary conditions. So boundary number 1. X equals 0. I have to have psi of region 1 at x equals 0 has to equal psi in region 2 of x equals 0. There's another condition that doesn't apply. How does that work out? Another condition that doesn't apply because of the discontinuous, which is a non-real boundary. That's why the second condition doesn't apply. The normal second condition is that the slope is continuous. So unless infinite boundary, which is our case here. We start with the infinite boundary, and then for all other cases, we don't have it. So in this case, we just have the condition that psi 1 equals 0. So that replaces our second boundary condition. But that makes life easy with that replacement boundary condition. So what's my function? I wrote it up at the top. What's cosine of 0? What's sine of 0? So I have 0 is equal to d, the end, right? So this required d is equal to 0. So that's what I got from my first boundary condition. So now I can rewrite psi is just g sine of kx. It's getting simpler. Now let's go to our second boundary condition. I have my same two conditions. So I'm going to have psi on one side equals psi on the other side. But because of the second boundary condition, that's equal to 0. And so that's going to give me g sine of KL equals 0. Know what this didn't tell me? It didn't tell me g. What does it tell me? If g is 0, what do I have for my result? Psi is 0, what we call the trivial solution. If psi is 0, that means there's no particle in the box because the probability of finding the particle anywhere is 0. So we throw the trivial solution away. What's the other solution? Not k is 0. We have to have sine of KL is 0. So that's going to be some integer multiple of pi. Because sine of 0, 0, sine of pi, 0, and so on. So now I have the energies uniquely specified. There's only certain energies allowed because k depended on energy. So we go back to our definition of k. K was equal to the square root of 2m e over h bar squared. And that has to be equal to n over L times pi. So square everything. I put a subscript on the n's now because there's only certain, or on the e's, a subscript of n on the e's because there's only certain energies allowed. And so there's my energy states that are allowed. So we can go in right now and we can just put in what the value for L is, the width of the box. And then that, h bar squared, pi squared over 2m L squared, multiplied by 1 squared is my ground state, the lowest possible energy. Notice it's not possible to have 0 energy. This equation doesn't include 0 because if k equals 0, then I have sine of 0. Once again, what's my wave function? 0. So it doesn't include energy equals 0. It's not possible to have a particle in a box and have that particle with 0 energy. It has to be moving. So, it has to have energy. So the minimum energy is with n equals 1, or then we can put n equals 2. It would be 4 times the energy. n equals 3, 9 times the ground state energy, and so on. So we've now calculated the energy states. There is still one thing left to do. What's the probability of finding the particle in the box? If I have one particle in the box, what's the probability of finding the particle in the box? If I'm awake now, what's the probability that I woke up this morning? 100% or 1. If there's a particle in the box, what's the probability of the particle being in the box? 1. So that means that if I add up all of the probabilities of finding the particle anywhere in the box, it needs to come to 1. So that's what we call the normalization condition. And man, I got to add another page just for that. Seriously? Not about the bless you, about the fact that that it's, once again, it's because it crashed that I had to go through this the second time. My timing of this seriously could not have been worse timed. Bless you. Seriously? Okay, so I now have psi of x is equal to g sine of, and I'm just going to put it was KL. We had KL had to be equal to n pi, and it was here, I have to think, it was kx, so it's I'm going to write it that way. I took out the k and replaced it with something that has an n in it. So that's my psi, and then I have to have the sum of all the probabilities. Now we have to go back to what psi meant. Psi was telling me information about the probability, but how do I actually find the probability from the wave function? I have to square. Now, technically, I have to do the mod squared. In this case, g could be a complex number, and so I would have psi mod squared is equal to g star sine of n pi over L x times g sine of n pi over L times x, or g mod squared sine squared of n pi over L x. So that's going to tell me about the probability. If I want to know the probability of it being in some region dx, it's that. And how do I add up all of the probabilities? I have to integrate. So I'm going to have 1 has to be the sum of all the probabilities. There's your generic statement. Sum psi mod squared over all dx over all values of x. Now, in this case, it's real simple because what is psi going from minus infinity to 0? 0. So I can break this down into 3 parts, 2 of which are trivial. Well, the two on the outside are just zeros because you're integrating 0 over a range. It still gives you 0. So it's just the middle one that is not 0. Now, if you do this integral, you find that there are some complexities to it, but it turns out that no matter what value n is, it gives you the same result. Actually, I think there's a pi in there as well. Let's go to the next page and see what it is. Nope, I was right. I wrote a here. A is equal to L. So I have A's there instead of L's. But my memory was right on that integral. So now we have these different wave functions. Question, Brady?
Can I see what you were on this slide? Okay.
So G square root 2 over L. Here it's square root 2 over A. You'll find all kinds of nomenclature for what we call the width of the box. But we have specified a wave function completely now and the energy levels completely. And, as luck would have it, that is the same as what I found, which makes me feel good, especially because I had that minus sign that I forgot until halfway through the derivation. Over here, we have what the wave functions look like. So if I plot sine of pi over ax, I get the blue line. If I plot sine of 2 pi over ax, I get the red line, and so on. So those are telling us some kind of information. What we can take from this that we know how to do is to square these. So if I square these, what do they look like? It still looks like a sine wave, but now it has, if we look at n equals 1 where it has half a cycle, it'll have a full cycle. It'll go from 0 to peak. It goes from minimum to peak to minimum again. So it's going like this, which is one complete cycle of a sinusoid. Whereas what was drawn in there is only going from those two spots I just marked. So we would have something like that. Where are we most likely to find the particle? At the peak. And it could be a positive or a negative peak because when you square it, they're all going to be positive. So I'm marking actually I should have gone like this. The positions where you're most likely to find the particle. Those positions vary depending on which state you're in. What's more interesting to me is where you can't find the particle. What's the probability of the particle being at the wall? 0. Right? The particle can't be in the wall, at the wall. It can come vanishingly close, but it can't be at the wall. In the n equals 1 state, that's the only one. N equals 2, it can't be at the center. N equals 3, it has 2 locations it can't be. N equals 4, it has 3 locations where it can't exist. Now, here's a question I asked my teacher when I was in college. I said, wait, now you're saying if it's in state 2, n equals 2, and we make a measurement and we find its position is where that dot is. And then it stays in state 2 when we make another measurement. Can it be on the other side? And he says, yes. And I'm like, but how? If there's no probability of being in the center, how can it move from one side to the other? Does that question make sense as far as what the question was? And the answer is because we're not talking about a localized particle. We're not saying, here's the electron. We're saying this electron is in the box, and if I measure it, my probabilities of finding it are shown by this sine wave. But it's really filling the box. except for, probability of being different places is different amounts. And so when I measure, I could find it here, then I could find it here, because it was covering everything just with different percentages there. When I measure, it forces it to be one place, but then when I stop measuring, it be wherever it wants again. And it covers the entire range. So it's part of the wave treatment of a particle that says, even though there's a forbidden region, it could, when you make a measurement, you could find it crossing that region because it's filling both sides. Now let's look at what, I said this carries all the information, right? All the information. Well, how do I find something from this then? The expectation value for position. Expectation value is what we mean in physics for if I make a measurement and I take the average of all of the measurements, what is it? So it's not actually value I expected to find necessarily. It is the value of the mean. And so the calculation for the mean is done like, let's say we have an operator. I have x with a hat over it means the x operator. Such that the x operator acting on my wave function is equal to the x value, no hat on it, times the wave function. That's the way these operators work. The operator acting on the wave function gives me the value times the wave function. Now the x, because we're in position space, the x operator turns out to be just x. The momentum operator is not p. The momentum operator is minus I h bar d dx. And that brings up other issues that we clearly don't have time to do. But now we can say, okay, where am I likely to find the particle? What's the expectation value? And what we have to do is take the integral of the actual position multiplied by the probability dx. But probability is psi star psi. And so this turns out to be as a general form like that. But x operator acting on psi should give me back x times psi. And so this is going to be equal to, in our case, integral from 0 to L. We now have done what G was. The G mod squared was L over 2. So I'm going to put that out front. X sine squared another fine integral. One that we're not going to do here today. But if you go and do the integral, you find that regardless of the value of n, you find the expectation value is at the center. You find your answer is L over 2, regardless of what n is. And then if you come and look at this, you say, but the chances of being at the center in the n equals 2 state is 0. But the expectation value is at the center. How could that possibly make sense? Yeah, it's the average. You have a symmetric distribution with half of it on the left and half of it on the right. Symmetrically, it means the average is going to be at the center. And so you'll never get the expectation value if it's in the n equals 2 state. Or if the n equals 4 state. You'll never get the expectation value. But if you take a lot of measurements, you'll find the average matches it. Okay, I have 1 minute, so I only have a few more statements on quantum physics, and then you'll be done with quantum physics. We have learned about normalization. That was the probability of finding the particle equals 1. In all space, I should have said. We learned about boundary conditions. Now we have orthogonality. We have words in math and physics that you don't use other places, and this is one. Orthogonal is a multidimensional equivalent to perpendicular. Now we have another three-dimensional equivalent to perpendicular. What was that? Normal, right? So we have three-dimensional equivalent to perpendicular of normal. Orthogonal is multidimensional. Yeah. So orthogonal in 2 dimensions is equivalent to perpendicular. 3 dimensions, normal. In 4 dimensions, well, I don't have a term for it other than orthogonal. So these solutions, we had solutions for n equals 1, n equals 2, n equals 3. We had all the different size that went with those. Those have to be orthogonal, which means they're, two-dimensionally perpendicular to each other. When we do an integral of psi star psi, that's actually, very technically, the integral of psi dot psi. If we do psi dot psi, and it's normalized, that has to be 1, right? That was our normalization condition. But what if I take psi 1 dot psi 2? If they're orthogonal, what's psi 1 dot psi 2 going to be? 0. And so the orthogonality condition says that when I do an integral of psi star sub n, psi sub m, okay, I put them opposite, psi star sub m and psi sub n, that's going to be 0 unless n equals m. And so that gives us this here, the Kronecker delta. The delta subscript mn is a shorthand notation that means it's 0 unless m equals n. So that equation there is actually combining the normalization condition, the integral of psi star psi has to be 1, understanding that means with the same subscript n, and orthogonality, if you have 2 different solutions, n equals this and n equals that, and they're not the same number, then it has to be 0. We are out of time, so the last slide was just talking about how we make superpositions. That's where the Schrodinger cat comes in. Okay, I'll see you in lab. We're going to be working with radioactive materials today. Don't bring food or drink at all, not even in your bag, nothing. And I'll make a big deal out of it in class.